Welcome everybody, and a new special episode or a guest episode of our never-ending journal club, as we call it. And today we have the pleasure to have Johannes, Kleiner, and Tim Ludwig with us for this, which are the author of the paper that we discussed last time. And so I would say that we can start with a round of self-introduction, so that we all know who we are. No, maybe I can start. So my name is Francesco Ellia. I'm a postdoc at the ATR and adjunct researcher, I think, at Monash University under the supervision of now Tsuchiya.
Yeah,
I can
cool.
continue.
Oh,
I'm
you
sorry.
sorry.
No, actually, yes. Our guest should continue. So yes.
No, sorry. I was
go ahead.
just yeah. Okay, yeah. Thank you very much for having us, first of all, and for reading the paper. Independently of how hard your criticism is gonna be in just a second, I'm really grateful, and I think I speak for both of us, Tim and me. We're really grateful that you even read it. You know, I know it's difficult work, and it's not at all to be taken for granted that people try to read papers. So that's wonderful. And yeah, thanks for having us. As for myself, so I'm currently on the one hand a postdoc in the Institute of Psychology at Bamberg University, and on the other hand, I'm still finishing my second PhD, which is officially in neuroscience and unofficially in mathematical philosophy. So it's submitted and the defense is coming up soon, so that second chapter of my life closes. Originally, I'm a mathematician by training. I studied physics, did a PhD in math, was a postdoc in physics for a few years, and during that postdoc, I started to work on consciousness, at which time my boss told me that I should really think about whether I ever wanted to have a job again in physics, which I decided I probably didn't. But so here I am, and as you of course know, maybe not everyone, so my focus in consciousness science is really on like the formal questions. And what we're discussing today is a first approach of an idea that originally goes back to Ryota Kanai. So he suggested this once, couldn't we have like no-go theorems in consciousness science? And one or two other papers of mine have this sort of flavor, but this is the first time together with Tim that we actually tried to do a thorough no-go theorem. Thanks for having us.
Yeah, also thanks from my side. So I'm Tim Ludwig. I'm a postdoc currently in philosophy in Karlsruhe, KIT Karlsruhe. Originally, I was trained as a physicist, also in Karlsruhe, and then did my PhD in physics there. Was still employed as a postdoc in Utrecht for some time as a physicist, but for about like 1.5 years ago, I switched to philosophy, focusing mostly on philosophy of physics or philosophy of science in general, and trying to figure out ways to make it useful for sciences or more useful for sciences. So and my activities in the consciousness science field is mostly motivated by that, like trying to see what can we bring to consciousness science as an empirical science from the perspective of philosophy. That's basically. Thanks.
Okay, I'll go next. But so I'm Angus. I'm a postdoc at NAO's lab, so at Monash University, and I guess at opposite to Francesco, like adjunct or whatever, associate for ATR. And so my undergraduate training is in psychology and computer science. And I've sort of like tried to kind of combine the two, and now I'm like focusing on like trying to test integrated information theory, or like trying to find markers of consciousness using like just exploring many different types of analysis methods. So that's where I'm at right now.
Yes, and my name is Aniko, and I recently finished my PhD at Monash University, and now I'm a postdoc in the same lab working with Tsuchiya and Angus and Francesco. And my background is in psychology, and then I moved towards neuroscience. So hopefully I can represent that area today.
That's awesome. So now that we made the presentation, we can actually discuss the paper. And to answer Johannes, this is really not about making criticism about the paper. It's really about we really want to understand the paper, because actually maybe this could be a first brief comment. Something I really appreciate about the paper, and I think it's really telling of, especially after this round of introduction, where we all have different backgrounds, like quite different, right? Mathematician, computer scientists, psychologists, philosophers. We really have all the fields. And this really, to me, reflects one of the beauty of our field, which is consciousness science, which is this highly interdisciplinary aspect. And something I really loved about the paper is that even though I don't have a background in mathematics, for example, it was really, it's really stimulating to read papers that come from such different angles, right? Like maybe the day earlier, I read some kind of classic psychological study, and then the day after some kind of completely abstract philosophy. And some of the beauty of our field is that we have all these approaches combined, but obviously this is also a difficulty, because for example, as you mentioned, the paper is quite technical, and for me personally, it was quite cool to get into really the nitty-gritty details of the main argument. So maybe the first thing I would like to ask, but please feel free to interrupt me at any time, to jump in with question, or just tell me if I'm talking too much. There are two major things. One is if you guys could spend some words on dynamical relevance, and then basically this is the entire paper. So dynamical relevance, and then why this would be a problem for artificial consciousness.
Yeah. Should we start with a qualitative idea? Like, do we have a whiteboard which we can use? That would be great.
Sorry?
Can we use a whiteboard, like to have a shared view of something?
Wow. I have seen other people do that.
Okay, no.
I think there's
Let me know
another one. Yeah, or maybe, yeah.
Or if you could just like use something like Paint and then just share screen. Unless you want to like have multiple people drawing it at the same time.
Okay, I think I can also explain it in words then. Let's try to do it.
Tim, if I can, so I think it would be very helpful if we get some sort of, I mean,
Okay.
if I understand correctly what you wanted to present. So one option would be if Aniko, if you could make me a co-host or allow me to share my.
Yes.
No, sorry, the Linux is saying I can't share. Darn it.
Okay.
Need to install something. Sorry.
Okay, maybe I can share a blank screen and then you guys can annotate.
Oh,
on
that's
it, right?
a good idea. Yeah.
Yes.
That sounds great. Yeah.
Just 1 sec.
Yeah, sorry. I think I should have asked that before we started recording.
It's okay.
It's okay. So the people that will watch the video will have the proof that this is a live conversation. It's not prearranged.
Okay. They can still get a coffee or do whatever, or like, yeah.
Okay. Almost there.
Timmy, if you're in Windows, right?
On Mac.
On Mac. Isn't there like a drawing app on Mac somehow? Or Windows has this integrated drawing app?
There are some, or at least one, but it doesn't work with my pen.
Okay, I see. Darn it. Yeah. Cool. Yeah, that should work.
Okay. Now I have a white screen, but I don't see any way to draw on it.
So do you guys maybe see an annotate icon? So something.
Unfortunately, not.
I have like a little drawing icon. So on the Zoom toolbar, usually there is like an annotate section. Or is it only me? Maybe I can make all of you host, and then you can also have. Or maybe that's
I don't have the annotate window today,
but
I know that sometimes I have it.
Maybe
same for me. Yeah.
Maybe you can try to make
everyone co-host now. Let me. just do that.
Oh, oh, nice. Thank you very much.
Yeah. You would
So
think that after like 4 or 5 years we have been using Zoom, and
Yeah, I
have
think it's
learned
getting
that.
changing from time to time. But I still don't have anything to draw, I think.
Me neither.
Same here. Maybe the university disabled it. Do you have anything that works with your pen, Tim? Like which you could share?
Like, yeah,
Yes,
like, so you
I
don't see,
think
you
so.
guys don't see this section here.
You're talking about like this
No, we
control
don't see
bar, right?
anything there. Yeah. Okay, let me.
I don't have that. Yeah.
I think this is it makes me so comfortable right now that we have this little bit of time. Really, I'm not kidding.
Okay.
Yeah. Just to solve a
I
problem
mean,
together,
I
you
have
know.
something, but let me try to see if I can.
Oh wait, okay, sorry. I have found something.
I see it.
Oh, nice. Yeah.
Works.
Yes.
Can you,
Okay,
do you
there
have that?
was.
Oh, perfect.
was-
Yeah. Now I can.
There was an annotate or an enable annotation for others.
Okay. Great.
Cool.
The more you know. Yay.
Nice. Yeah, there we go.
Okay, great. Thanks. Yeah, then let me maybe start with some very general things. I assumed you know like the concept of formal systems, or maybe just explain it very briefly. So a formal system is anything where you can draw some conclusions, make some next steps just by formal rules. For example, a standard example would be the rules of formal logic or of standard formal logic. There are different types of logic, of course. And what our paper is about, in a way, or one way to view our paper, is about the relation between formal systems and implemented physical systems. And let me just start very abstractly about a formal system. Let's say we have an axiom which just says A. So A is like for some statement which can be true or false, and we have a second statement which says a second axiom which says not B. So not another statement. And then we can use the formal rules of logic. Formal rules of, let's say, standard logic. Standard logic. To conclude that also not A and B. With parentheses, of course. So this would be just a formal conclusion, right? So there's nothing that can go wrong on that side. And that's the formal system part. But then there's also like, if we want to implement such a thing in a computer, then we would build, for example, a NAND gate. So we would have like some input representing A. Let me try it like this, like schematically, but I'm now thinking about like the real physical thing, not about the schematics here. It's just to represent the real physical thing which we would implement. So we would have A and B, and we would have not A and B as output. And let's say we have 5 volts representing that A is true. We have 5 volts as input here. We have 0 volts as input here, representing that B is false. And then we would get out 5 volts representing that not A and B is true, right? This is how a NAND gate should work. Is that kind of clear what I'm talking about with NAND gates?
Yes.
So NAND is just short for not AND. So this is A and B, and the N in NAND. Let me write it down. So it's NAND. This is AND is A and B, and then the N is for not that. So this would now be the physical implementation of such a NAND gate, or like representing a physical implementation of a NAND gate. But here is like something that we might wonder about is, okay, could there be any other influence? Let's say, could there be consciousness becoming relevant and suddenly turn, and it's not necessarily consciousness, but could it suddenly turn like this output of 5 volts here? Could it turn it into 0 volts? Like, could it make it false because of consciousness or because of anything else? And the first thing to observe here is that this you would never accept on the formal rules side, right? So you would never accept that actually here, instead of concluding not A and B, I conclude let's say A and B. Oh. I conclude A and B. And then you would object and say, no, that's not true, because so I started with A and not B, so I cannot conclude A and B. And then I say, oh, but consciousness was responsible for that. You would never accept that. And why wouldn't you accept it? Because it doesn't fit to the formal rules of standard logic here. So this is something you would have to refuse in any case, because it would violate the formal rules, right? And then, however, on the other side, what might happen is actually that this NAND gate here is broken, in the sense that it is physically possible that you have a thing, you've built a thing which you think is a NAND gate, you put in like 5 volts on the one side and 0 volts on the other side, and you get out 0 volts as a result, which should not happen, but it could, right? So it's not, then what you thought it's a NAND gate, but actually it turned out it's not. And this is like a place where consciousness could come into play, let's say. So let's say this is, if it was a conscious NAND gate, then what the output is here, I mean, conscious like as a collection term for anything other being relevant, which we didn't mean to be relevant here, at least for the argument. And that it could also be consciousness, that's like a separate question. But like there's something which causes the output to be different from what you would expect. And that could happen in principle for a physical system you implement. But in practice, what you need to do is you need to check if what you implemented is actually true. So you want to exclude that option by verification. So you want to make this is impossible by having the verification step. Verification. So what is this verification step?
Sorry. Yeah, if I can, just to be sure that we are on the same boat, setting aside consciousness for a moment, here at this logic gate could simply be the case that I built it wrong, right? Or maybe it's a little bit faulty, right? It's so, and
exactly.
simply I implemented a different kind of, instead of an AND, some other operator, and the result is different from what it should be, right? That's the point.
Yeah, exactly. So there could be anything going wrong. So that's what I meant. So sorry for introducing the term consciousness here. It's anything, like the C now stands for anything that causes the result to be different from what we would want the result to be. So it's not necessarily consciousness yet. So it's just the C is for anything that causes, just saying it again, C is for anything that could cause the output to be different from we would want the output to be. And that is what we need to exclude in computers with verification processes. So there are two types of verification here. I would say, let's just unify them. It's like the post-silicon verification would be more important, which is checking if the physical thing, like the physical chip that was built, is actually doing exactly what it's supposed to do, meaning if it's really implementing the formal rules of logic which we want it to do. That means the verification step excludes like the wrong outcome here. If the wrong outcome happens anyway, then that means we didn't build a NAND gate. So the verification step is, so if that happens anyway, so this is what we want to exclude by the verification step. If it happens anyway, then it's not an AND gate, right? So then it's not an implementation of our formal system. And if that would happen in a real computer, then whatever is going on is not actually like a computer in our sense, because it's just doing something else. That would be a broken computer or a broken NAND gate in that specific situation. And that means like this verification step that ensures that either the system is broken or it follows the formal rules of standard logic in that case, or whatever the formal system is we use. Could also be like some piano axioms for natural numbers, or whatever you would want to come up with as a formal system. And that means like this only leaves two options: either the NAND gate, or like generalizing to a computer, either the processing unit works as it's supposed to work, or it's broken. These are the two options. And if it's broken, then it's no longer a processing unit. It's a broken processing unit, if you want, but not what we meant. And if it was a broken processing unit, then let's say what we would program on it is actually not clear. It's no longer clear what's happening, because we using a programming language, we assume that our processor is doing what it's supposed to do, and not some random stuff or some arbitrary stuff, let's say. So these are the basic inputs in, like, at least from an abstract point of view, these are the basic inputs in our no-go theorem. So on the one hand, we have the formal system, where we would never accept like anything violating the formal rules, be it conscious or not. There is no way like violating these rules, because there's not actually a process happening. It's just our way of concluding from statement 1, statement 2, we conclude statement 3 by following the formal rules. And on the physical side, to implement such a formal system, we need to make sure that the implementation is really implementing the formal rules, and that's why the verification step is important. But if the verification step is there, then just saying it again, it leaves only two options: either the physical thing follows the formal rules, or it's broken. And now going back, if I just continue quite quickly, like going to the C, like if we now interpret that C as consciousness, not just as an arbitrary source of things being broken, if it was like consciousness entering here, then it can also not play a role, or it would be a broken NAND gate, right? So a conscious NAND gate, if consciousness is relevant for what's going on, like dynamically relevant in a way, then that's not a NAND gate anymore, right? Is that kind of clear? And do you already see the relation to the no-go theorem, or should we go more into details there?
Just a quick clarification question, or kind of like going behind this kind of the assumptions here, because you say that, or in your paper you describe that this dynamical relevance is relevant for the temporal evolution of the system. And so in this example, the temporal evolution would be, oh, I will also annotate a bit. Oh my God. Yes. So you would be like time step 1 would be like this, and then time step 2 is this. So in a way, this is where the temporal evolution happens.
Yes. Yeah, that's how I would view that. I see Johannes is agreeing. Yeah.
Mm-hmm. Yeah.
So we have the input, like if you think about it in terms of physical evolution. So there's some input voltage or current coming in, and then like the NAND gate does something to it, and then we'll create the corresponding output. So that's like temporal evolution in that sense.
Okay, I think that's good to clarify. And then I might have some questions coming back to it later on, or more like high-level questions, but maybe the others have more clarification questions. So I will let you guys talk.
So maybe, Aniko, if you can, okay, great. So for me, up to this point is very clear, and thank you for your explanation, because especially on the physical implementation, I think this helps me. But I still fail to see exactly like how does this connect with consciousness? Like because so maybe it would be nice if you could spend some extra word on what you define by dynamical relevance, because I think these are there are two at least completely distinct topics, right? On the one side, there is basically how computer work, which is obviously important for the topic of artificial consciousness. And on the other side, there is what computational functionalist theory of consciousness could require in order to have consciousness, and in particular, what could require in a computer in order to have consciousness. So these are two separate issues. So the computer part, I think I got it up until here, but I failed to see the relation with the computational functionalism part.
Can I try to take this, Tim, or do you want?
Yes,
would
please.
you rather?
No, please.
You can also. Okay. I mean, I think this is something that you were going to explain anyway, and I think it would be good if you do anyway, even though I'm saying this now. So I think there's this. So I mean, basically, there's this question. So let me try to see if I can draw as well. So there's this question about, okay, so how does dynamical relevance come in, and how does it relate to computational functionalism? And basically, just as a reminder, so the theorem which we have basically says, if consciousness is dynamically relevant, then AI systems, and that are systems which run on so current AI systems running on the current sort of technology, which is verified, can't be conscious. And the important part here is that dynamically relevant is really a property of a theory of consciousness with respect to another theory. In the theorem, we apply it to the true theory of consciousness, which we don't know yet, but it is a property of a theory. And the idea is basically just this. So here you have something like it's a formal model. It's the same sort of thing you would have in a theory. So that is just let's call this model M here. Yeah. And now basically there are two options. And basically, and the first option could be, and two options for a theory of consciousness, TOC. And the first option would be that consciousness is, so the theory of consciousness posits that consciousness is identical to something which is already in the formal system. Theories are descriptions, models are descriptions. So for example, it could posit that consciousness is identical to, I mean, to the extent that it makes sense even, but something like to the NAND gate, yeah? It could be, the theory of consciousness could basically say, the postulate, whenever there's a NAND gate in reality, there's consciousness in reality. That would be a computational functionalist theory. And then the other alternative is that the theory of consciousness posits that consciousness is something in addition, or you should say something else. Yeah. Oh, sorry, this didn't work. What else? Okay. And the important point is that, like, before we go to the actual sort of formalism or whatever, or the context of the paper, is that if consciousness is already in the formal system, right? If the theory of consciousness says, well, consciousness is just something that's in there already. It's basically just introducing a new variable and saying that denotes existing things. Well, then there's no problem, right? Then you can take the physical system that you built already. It's verified to adhere to a formal system because consciousness is already in the formal system, just that we didn't know it when we produced the processor. There's no problem. So in this case, you can have consciousness. And in this case, that's a case where the theory would postulate consciousness as not dynamically relevant. Not dynamically relevant. So the precise thing would be so the theory of consciousness posits or describes consciousness as not dynamically relevant with respect to this model M. So now, what in the other case? What if consciousness isn't something that's literally already in there? Well, in this case, there are also two options. And can we move this whiteboard? Does anyone know whether we can move this?
Probably not, because it's a shared white screen, right?
Oh, it's a shared widescreen. Okay.
Yeah, I don't know if I can do that.
It doesn't look like it. Yeah. Okay. Well, anyway, so I'll just continue here. So there's another two options, and then in the second case, that means you introduce a new variable that isn't already in the system, right? And now you can do that in two ways, and I'll just squeeze it in here again. You can either introduce the new variable in such a way that something changes, right? The theory of consciousness says, well, whenever consciousness does appear, then I'm going to propose some slightly different dynamically evolution than I did before. So that would be the case where you have dynamical relevance. Or the theory says, I'm going to introduce a new variable, but in a sense, the new variable is just a function of all of the old variable. That's more or less the case I had above. The only difference is that it's not literally in there. It's a new variable, but it's just a function. It would be a function from all of the old variables or all of the old expression to new expressions. And in this case, this would be no dynamical relevance. And the point of our paper now is if the theory proposes that consciousness is like there's a new variable, it relates to consciousness, and that new variable changes the dynamic of the formal system, then because the physical system was built to adhere to this formal system, but the theory of consciousness changes it around a bit, the physical system can't do what the theory of consciousness wants it to do. So that's I think one way to see the intuition. And I'll just one more sentence and then I'll give it back to you, Tim, or everyone else. So one thing I really care about is it's very easy to think about this whole problem if consciousness were something non-physical which has had a causal effect on the physical. And that's a valid way of thinking, but it's not the only way and it's not the major way. Because this whole problem also appears for if consciousness is something completely physical. And to give you an intuition of why that is, like the C which Tim drew in here, right? We could say it's not consciousness, it's cosmic particles, right? So there's another theory. We have our formal system that's just for the computer, you know, just the instruction set architecture or whatever, just the thing the computer is supposed to do. But now we can also take into account cosmic particles, cosmic rays, which are hitting even right now, cosmic rays are changing around bits in your computer. And if you're like on the ISS, it's much, much more intense. So there could be another theory that describes cosmic rays and computers. And, or another sort of theory is a bit of a strong word, it's another model, yeah, another way of describing these things. And according to that broader theory, there would be things that attempt to change the dynamics of your physical system. So in other words, the model that describes cosmic rays and the CPU architecture together would posit cosmic rays as dynamically relevant for the CPU architecture. And CPUs are built in such a way that they detect these bit flips and change them back, right? Error correction. And that's just an intuition to see that this process is fully compatible with physicalism. The point being is just that your theory might want to posit something that is not already in your formal system. And if it does so, and that what it posits has some sort of influence, then you can see that, that the PU can't have that thing, right? Maybe before we go to question, can I ask Tim, are you happy with that explanation or did I miss something important?
I'm perfectly happy, so sounds great.
Okay.
This is great. Maybe now I understood the main claim. So let me just see if I essentially probably what I'm missing is at this point is the post-silicon verification. So if I understood correctly from your explanation, you're saying that essentially what post-silicon verification does is whenever the system, so to say, deviates from the trajectory that it should follow, it is a process or a procedure done to ensure that the system basically has some dynamical constraints.
I would not fully agree. So it's not like it's more a conceptual thing. This post-silicon verification. So it's actually done as far as I understand. But like there's at one point there's a verification step if like your NAND gates in the processor or whatever is in the processor, if those things implementing some formal rules of logic, for example, if they are really doing what they are meant to do. And only if that's the case, you are allowed to call the resulting thing a working processor, let's say, or like a processing unit. If the physical thing would not do what it's meant to do, then you would need to call it a broken processor. And AI systems, that's an implicit assumption, only run on working processors, not on broken processors or broken processing units. So if we would program an AI and let it run on a broken processing unit, we have no idea what's going to happen, because like the programming code and the physical, like what's going on in the physical world, there's no clear connection anymore. So we couldn't call it we couldn't reasonably call it an AI system, because there's just no understandable connection between the two. So that verification step, even though it's done once, it just basically defines what would be a working, like a properly functioning processing unit. Is like to be a properly functioning processing unit, it needs to pass the verification step. And if at some later point it would deviate from what it is supposed to do, then we don't recognize it in a verification step anymore, like in this post-silicon verification, but we would know that now the processor is broken, because we know it's not doing what it's supposed to do. That's the point. So it's not so much about the error correction, which is also important. So that's why Johannes brought it up. So the error correction is part of the processor, as far as I understand, or like of,
I think the functional.
Actually have of the function, yeah.
Functional verification.
Pardon me?
Yeah. So I'm not sure if this, should I extend this or explain this part?
Yeah, if you can explain it, that's better. Yeah.
There's a danger that we're just giving two answers to every question, and that take a lot of time. But I'll do it one more time. So I think it's really helpful to think about this, because I think is it okay, Francesco and Aniko and Angus? Can I real quick? Okay. So just real quick.
No, sure, you guys have all the time. Yeah.
In terms of levels. So basically, I think it's really important. So like building CPUs is a quantum thing. Yeah, you're using semiconductors, they described by quantum theory. We don't realize this, or I didn't realize that before I studied physics, but like literally you're using quantum tech all the time. So here you have the quantum system, which is basically like not a tiny, like not this laboratory sort of quantum system, but a condensed matter quantum system. So Tim is an expert, by the way, on condensed matter physics. And so you have this quantum system, yeah, condensed matter physics. That's the theoretical level that describes how you're going to build the chip. And then what you have is, in addition, you have this, let's just call it M again, you have this formal system. Realistically speaking, it's something like you have a model that describes the instructions that the CPU is supposed to carry out. It's called the instruction set architecture, basically. And then what you do in the first step is, so you basically see, okay, how can I make sure that on a theoretical level, before you build any sort of stuff, how can I make sure that the quantum system that I build in such a way that it implements the logic that I want to? And this first part is called functional verification. It's a purely theoretical endeavor. There's actually 4 types of verification, but I don't know the others very well. So this is just functional verification. And to my understanding, I have never worked in this industry. That is the level where error correction codes play a role. So you want to make sure, that like half of the energy that your processor uses is energy that is basically wasted because of dissipation. To give you a very concrete example, there's the gate oxide layer, which is where electrons are not supposed to go through. And in modern computers, this is so small that they always tunnel through. So you waste all of this energy. And that's why you need a very good design of the processor that makes sure that because of all of these errors, nothing strange has happened. And that is so on this level, we have the functional. So this is the functional verification that happens here. And once you have the functional verification, you have a concrete plan of how you can lay out, how you can etch your processor in practice so that it would carry out the system in theory. You have a plan of how you can do it in practice that is theoretically verified. It would implement the logic. But now you go a step further, and now what you do is you actually build the thing in practice, like you etch it, you go through the whole process, you spend your 500 million or whatever to get your CPU or GPU. And in the second step, you literally take the physical system and check whether the physical system actually does what you want it to do. And that's basically making sure that the whole production process didn't go, nothing happened into the production process that you didn't want. No deviation from the theoretical model. And so the end result really here is a physical system, and that physical system is also guaranteed to adhere to that logic. And the second step is called post-silicon verification, because post-silicon meaning you actually built the thing in silicon. Is that helpful? Or does it even answer the question?
Yeah.
And again, Tim, sorry. Yeah, I should.
No, that's perfect. Thanks for jumping in.
Helpful answer. Yeah.
Yeah, I think maybe this adds. The second question that I had is, if going back to what you said before, Johannes, you basically show 3 cases for a theory of consciousness, right? And if could you make any example of existing theories that we have and that we know to help us map these concepts into what we know, if there are theories that follow these constraints.
Yeah, I'm happy to answer, but this is the last. I really want. I have a tendency, because I'm very excited about this stuff, to always try to add something. So it's the last time I'll, like, if there's a question to Tim, like, Tim, it's your. I shouldn't add something. Sorry about that.
That's great. Please continue.
Yeah. But I don't want to talk too much. But okay. So actually, I should say 2 things. The first was, so actually, there's only 2 distinctions. This was really a problem in the way, or like a caveat of the way I explained it here. The distinction is only either you have a theory that's dynamically relevant with respect to a reference theory, or you have a theory that isn't. So in this example, which I drew, sorry, that was my pen. The top cases, so there's basically 2 cases where you have dynamical relevance. Oops.
Yeah.
So, okay, now I have a zoom bug. Let's try to see. So yeah, you know what I mean, right? There's this case, which is not dynamically relevant, and that's also in this case. They fit together.
Yeah. Right.
Okay. So this is the first thing. And then the second thing is, now it's super interesting to think about current theories. And there are a few theories which are pretty clear on which end of the problem they are. Most theories are not clear. And I think I can explain why that is, I think. So let's talk about theory. So one theory that is very clear is integrated information theory. It is very clear because it's fully mathematically fleshed out, and it's not dynamically relevant. It doesn't posit consciousness to be dynamically relevant. Because you plug a system into the algorithm tells you what consciousness is, but it doesn't change what you plugged in or the dynamics of the system. The dynamics of the system play a role, but they're not changed. Or in other words, the transition probability matrix of the system just is whatever it is. So mathematically speaking, it is dynamically irrelevant, even though the whole conceptual apparatus, putting consciousness first, should imply that it is dynamically relevant. There's like a mismatch between conceptual idea and formalism. But as far as the formalism is concerned, I would say it's definitely not dynamically irrelevant. And it's definitely dynamically irrelevant. Another extreme example is any theory that posits consciousness to be have a causal effect and to be something non-physical. Or actually, to be precise, like any theory that posits that consciousness has a causal effect, independently of whether it posits consciousness to be physical or not, would be a theory that is dynamically relevant. But maybe just this one point, because I really care about this. So why is it the case that in so many theories you don't know, or we don't know? Like, for example, global workspace theory. It's not really clear how you should read the theory. Is it just saying, like, is the right way of reading to say, well, neuroscience describes there to be a global workspace, and we're not just saying that's the thing that makes consciousness. In this case, global workspace theory wouldn't be adding anything to neuroscience. It would just say that which neuroscience already describes already contains what consciousness is, and we're going to say what it is. Or is the right way of reading global workspace theory to say, look, neuroscience missed the global workspace. There should be one according to our theory. So let's look for it. Here's an additional, we're putting something forward that should be integrated in neuroscience as we know it. In this case, it would be a theory that's dynamically relevant with respect to the known neuroscientific theories. And I think that the 2 things are clear. It's unclear how to read the individual theories, but 2 things are clear. First, any experiment whatsoever always presumes dynamical relevance, right? if it were like if whatever you measure is already predicted by your best neuroscientific theories, excluding consciousness, you couldn't take this as evidence for your new theory. So I think in practice, we always think that consciousness is dynamically relevant with respect to what we knew before. But the other thing so this is the first thing that matters. And the other thing that I wanted to say, I think, is that like, why is it then that when we formulate theories, we always formulate as if consciousness weren't dynamically relevant? And I think this goes back to something that happened in the field longer ago, and that this is this extreme importance that people attribute to the causal closure of the physical, and they misinterpret this as the causal closure of known theories in what we call the physical domain. So in other words, I think there is a sort of taboo, and the taboo is to propose a theory, like to actively propose a theory that puts something new into the physical sciences, including neuroscience. And this taboo is not at all, first of all, this taboo is not what is meant by causal closure of the physical. You can make new proposals for what consciousness is. You can't call them physical or non-physical. It doesn't matter. But the causal closure of the physical doesn't attribute to if you make a new proposal of a new brain function. So this is the one. I keep on forgetting what I want to say, but this is the main reason. So one of the main reasons is that we're misinterpreting the causal closure of the physical. And then the other reason I wanted to say is that, like, if you go to the sciences like physics, or I think it's also true from other sciences, like nobody would propose a new theory where you add a new variable that describes a new phenomenon, and it's only a one-way connection. Like, for example, even with dark matter, which is matter in the universe that doesn't interact with everything we know, right? We still presuppose that it interacts gravitationally. Or even with dark energy, which is a form of energy where we have no understanding, we have no concrete understanding of how it interacts with any explicit matter. We still have it in our model in our cosmological model as something that makes a change, in fact, a huge change to what's going on in the universe. Or even when we study weakly interactive massive particles in cosmology, which is a model of dark matter, we still propose that there's some sort of interaction mechanism that changes maybe the distribution of matter and antimatter in the universe. So what I'm saying is, in the physical sciences, nobody would dream about making a new model where the new variable has only a one-way connection. Yet in consciousness, for what I think is a misunderstanding of certain things in physics or certain physicalist ideas, we tend to always try to do this. Sorry, long answer. Now I'll try to talk less.
No, that was great, actually. Very, very helpful. And by the way, when I read this paper, I had the intuition that it's somewhat connected to your early work about the unfolding problem, like when you generalize the unfolding problem, right? I think 100%. This is the other side of the coin. So
the unfolding, so I would...
Aniko,
this just a one sentence of this. The unfolding argument works only because IIT is not dynamically relevant. This is not easy to, or it's not like clear, like this is not something you can see in a sentence. It would be a longer discussion, but it's exactly related. The proof that Eric and I gave presumes dynamical relevance, even though we didn't have that concept. I only have this concept because of Tim. Tim is like, just a wonderful collaborator. I wouldn't be anywhere like in terms of these results without Tim.
Thanks. I can give the compliment back. So. Yeah.
Oh, that's beautiful. So just I don't know if Angus, you haven't spoke, so I might give you the chance, but then I also have some questions.
Yeah, so I did have some questions, and actually one of them got answered already. So it was basically the first option. There's two options for theory of consciousness. And the top one is like not dynamically relevant. Basically, I was just going to ask, what if the AND gate is already conscious? Then we can't really say anything, but that's fine. But I wanted also to ask, in your paper, you give an example when you talk about dynamical relevance about this red car, this car or something. And I think you talk about red seats not being dynamically relevant, right? Or something like that. Like
coloring.
Yeah, the color inside the car doesn't really matter for how the car moves. but I was wondering, what happens if you extend the space or the domain of potential outputs that the car has, or the behaviors that the car has? So maybe as an example, just to make it clearer, when you're considering cars and motion, you're just thinking about how a car like moves on the road or something. But if you expand that to then include also how it attracts consumers or something like that, or changes the way how the driver interacts with the car, then suddenly you've expanded the space of, I don't know how to describe it properly, but you've expanded what you're considering as part of the behavior of the car. So I was just wondering, can something like that be considered in this case as well, where you have this system like this AND gate, and it turns out that if you focus just on, whether it's creating an AND or not AND or whatever, but if you then expand it to how it might then, I don't know, change color across, multiple processes or something random, something weird like that, would this argument still apply? I'm not sure if it makes sense. So like just, yeah.
So I think your intuition is great. So let me try to distinguish different situations. Like the car example is very useful. Like first saying that the car example is very useful because it's something from everyday life which we can think about. It's also a little problematic because we don't really have a car motion theory or anything like that. So it's not a scientific, at least not in the usual sense, a scientific study to study the motion of cars. Of course, it's important in engineering and all that, but assuming we had like a classical mechanics-based theory of how cars move, like given the motor is running, like we have a classical mechanics theory of that. In that classical mechanics theory, the color coding of the seats would not play any role, right? It just doesn't matter. However, if, and that's how I understand your point, if you include that the car is not moving on its own, but there's usually a driver in the car, like driving the car, if you extend the theory of how the car is moving to include the psychology of the driver, then suddenly the color coding of the seats might become relevant for how the car is moving, because it actually is dynamically relevant for the behavior of the driver. So if you include the psychology and behavior of the driver in the car moving theory, in addition to classical mechanics, then this color would become relevant and or dynamically relevant for how the car is moving. I think we had it maybe in a footnote or something like that. Exactly this if the psychology of the driver is included. But it's probably hard to miss in the paper. But yes, so I think this is exactly a point to think about, and that's also important, like a point that Johannes usually like makes very strong, because like dynamical relevance, other than causal relevance, is not something saying something absolute about how the world is, but instead it's talking about the relation between theories. So you cannot talk about dynamical relevance without having theories in mind. Like, and that's why the car example is not ideal, because we don't really have these car theories, which is why we also gave a more scientific example with this electric circuit, like where voltage is equal to resistance times current, and then like you could ask, is the temperature, which is from a different theory, it's from thermodynamics, not electrical circuit theory. You could ask, is the temperature dynamically relevant? And it is, even though it's not like part of the circuit theory in itself. So, and it's relevant because the resistance of a resistor actually depends on temperature. If you increase the temperature, you will have a different behavior of the current if you apply some voltage, and vice versa. So that is a concept from thermodynamics being dynamically relevant for the resistance, a concept from electric circuit theory. That is, so you need different theories to talk about dynamical relevance. Going back to the car example, to have the theory, you would have like another theory of color perception, let's say quality spaces of Clark, for example. You could use, and then the question is like, is whatever is perceived in this color space, in this quality space for color perceptions, is that now relevant for how the car is moving or not? And if you have like a human driver, it's probably relevant. If you have like an automated system, then it might not be relevant. I hope that clarifies it a bit.
Yeah, I think that helps, but also maybe just to also clarify better what I was thinking, maybe instead of, so when we think of if we stick to the car example, we're focusing on this idea of motion, like we're considering how the car moves. But what if you change the domain in which you're investigating the car and like looking at how the car degrades over time or something? So nothing to do with motion. So you have your theory, which is based on motion, and then you have something else which would not be dynamically relevant to that theory of motion. Say like if the car is white, it reflects light, so it degrades less, or it takes longer time to degrade. And if it's black, it absorbs heat, so it degrades faster. Something like that.
Mm-hmm.
So that sort of thing might not be dynamically relevant to the theory that you have for motion, but basically what I'm saying is, if there's another sort of aspect which this theory which you're considering dynamically relevance towards or something, maybe there's something else, right? Like say if for this circuit thing or the processing unit, again, like instead of looking at the output of these gates, maybe something just like when someone buys it, are they more likely to throw it away and not use it, or use it more? So so it's very removed in a sense from the reference theory. And I'm just wondering if dynamical relevance has always to be with that sort of domain, or whether it's restricted to the domain of whatever that reference theory is interested in.
I see. Yes. So I think I understand your where your point is coming from. I fully agree with what you say, that actually that something can be dynamically relevant with respect to one reference theory, and it can be dynamically irrelevant with respect to another reference theory. And I think like where the problem or your intuition might come from is that our statement in the theorem might be a bit too short in a way. So if we say if consciousness is dynamically relevant, we are not specifying like the two theories, right? So in that sense, it's too short. Like in the proof, we think it should become clear, but it's not in the theorem itself. Or maybe we adjusted it, but like there are two reference theories which are assumed like to be relevant. Like one is the correct or true theory of consciousness, which would be one theory, and that must address consciousness. And then there's another theory, which is basically everything else, like whatever is going on in like the natural sciences, like basically all theories of natural sciences combined without consciousness. And then we have these two reference theories, basically everything except consciousness, and then the true theory of consciousness, which also describes the relation to that.
Yeah.
And there are two options. Either consciousness is now dynamically relevant for everything, for anything and everything else, or it's not. And if consciousness is dynamically relevant, it means it changed something in everything else dynamically. That is not necessarily the same as saying it's causally relevant. Even though it's related, because if it is causally relevant, then it will be also dynamically relevant. But the other way, it's not necessarily true. So causal relevance implies dynamical relevance, but dynamical relevance does not imply causal.
Yeah, that was actually my other question that I wanted to ask.
Okay.
Can I just add something small on the question we had right now? Because I really like the question, because this is starting to get at the point where you can see why is it a theorem, right? I mean, all we talked about right now is pretty intuitive, no theorem needed. Why is there a theorem? And the point is that the theorem does something that in my mind at least, and I think probably also in Tim's, is rather strong. And let me try to explain. So in the paper, we provide exact definitions of what these things mean. What is dynamical relevance of one theory of consciousness with respect to a reference theory? And then a second definition where we say, what does it mean to say that consciousness is dynamically relevant? And in the second definition, we say, well, consciousness is dynamically relevant if the actual theory of consciousness, yeah, which correctly describes consciousness, which we don't know, it's dynamically relevant with respect to some of the theories. Some theory in natural science. So it's a rather weak condition. We only require that there's one theory with respect to which it is dynamically relevant. It's very, very weak. So why is it that we can actually prove the result? Well, the reason is that dynamical relevance has a property that is not so easily seen. The concept, the property itself, has a property that is not so easily seen if you think about it just like this. And in the paper, we call this a lemma, and it's called dynamical relevance passes downwards. And so what it intuitively means is that if you have a theory, so maybe, sorry, let me add one second for context, one sentence for context. So we all know the concept of reducibility. You know, you might have one theory that's reducible to another theory. And there's, in philosophy of science, there's actually various distinctions of how you could flesh that concept out, you know, what is important, what not. And what we do in the paper, we work with a comparably, or I would say maybe rather minimal condition. Not sure if it's really the most minimal, but like it's very minimal. And so what we say is, and like in retrospect, I think now we have a good term for that, but we didn't really have when we wrote the paper. And we could call it dynamical reducibility. And so it's just like you have one theory, let's say, like just to give something concrete, maybe a theory of the brain. And then that theory reduces dynamically if you can find a function that maps states to states. So like the brain, sorry, I didn't finish. We have a theory of the brain, let's say neurons, or let's make it very simple. Let's say we have a theory that describes one neuron, and then we have the actual quantum description of the molecules of the neuron, right? And then we say that the neuron theory is dynamically reducible to the quantum theory if and only if there's a function that takes quantum states and maps them to state of the neuron theory, you know, like a whole range, huge amount of quantum states correspond to maybe the on state. And then also, like when you have this function, the dynamical changes of the quantum state, right, it evolves, like agree with the dynamical changes, the evolution of the neural state. So in other words, just like to make sense of the idea that a neuron, for example, described by a couple of differential equations, really is like a more fundamental object. It's just a higher order theory. So we call that dynamical, we would now, I think in retrospect, call this dynamical reduction or dynamically reducible. And now what you can show formally is that if you have a theory A, and this is dynamically reducible to a theory B, then if consciousness is dynamically relevant with respect to A, it follows by logical force, by necessity, that it's dynamically relevant with respect to B. You can also make sense of this if you think about it long enough, but we show it formally. And now this is what allows us in the theorem to say, well, if consciousness, so among the scientific theories, which we assume are dynamically reducible to one theory, even though we might not have this, then, so basically, if consciousness is dynamically relevant with respect to any of those, you can go down, and then going up is easy, and so you can basically go to the CPU. That's what the formalism shows. So meaning if you know that consciousness is dynamically relevant with respect to, let's say, a neuroscientific theory, if that theory is reducible to the physical theory, then you can go down and back up. And there's two remarks that are important. The first one is, why does it make sense to assume this very weak form of reductivism? Well, it makes sense because it's compatible with weak emergence. And as soon as you assume strong emergence, which is like the next step upwards, then you have dynamical relevance anyway of consciousness. Strongly emergent phenomenon, by standard understanding of strong emergence, is dynamically relevant with respect to the emergent space or whatever you want to call it. That's the first remark. Now, the second remark is that there's actually a loophole in our theorem, which I think we only saw in retrospect, or at the very, very end, maybe, at the earliest time when we did the revisions. And that's a loophole that Christian List came up with. And I hope, Tim, correct me if you see this differently. And what could happen is that consciousness is dynamically to the wrong neuroscientific theory. right? So you have a neuroscientific theory. It's not this theory is not actually reducible to physics. It's just wrong. You add consciousness in. Consciousness is dynamically relevant. And now what happens is that the theory you get then with consciousness, that is dynamically reducible to physics. And that's an extremely important loophole. And the reason is that, so in the paper, we always talk about dynamical relevance is really just a statement primarily about the state of knowledge of theories. You have some theories and you have another theories. But now there's this wonderful blog post by Justin, maybe you've seen it, and I've wrote this reply, where, of course, you can think, well, what about the fundamental physical theory? If I'm like a hard reductionist, if I'm like a t-shirt physicalist, you know, meaning I think physics is basically described by an equation that fits on a t-shirt and the initial state of the universe back in the day, you know, like 14, whatever, how many years ago. And everything just follows. And then and the point is, because of this loophole, which Christian List saw from the start, it took me and us, I think, me at least 2 years to see it or something, 1.5 years to see it. Maybe Tim, you saw it, you probably saw it quickly once I mentioned it. But so because of this loophole, this all is like the whole theorem is even compatible with t-shirt physicalism, which before we saw this loophole, or I think still basically is a point where we really ponder about. I don't know, Tim, do you want to expand on this? Like this whole passing downward and like there's still lots of open questions there.
I would like to clarify a short thing, just very quickly, if you agree. I think it's not a loophole in the theorem itself. It's a loophole in the application of the theorem, right? So the proof of the theorem is not wrong. It's just like how to apply the theorem. That is where the loophole is. So if you assume like something, like if in the theorem, like the theory, the reference theory is actually a wrong theory, then it's like it's more complicated to apply it than we originally thought. So just wanted to clarify. And sorry,
it's a loophole. I'm sorry, it's a loophole in the sense I use this word because of the Bell inequalities, which is like the best sort of no-go-ish theorem that we have. And people look for those loopholes, which is like ways to get around the theorem. It's not saying the theorem is, Bell's theorem is just true. So how can you get around it? Maybe all of the neuroscientific theories are wrong. Then you would get around it.
Let's hope not. So on this, I think now I kind of understand a bit more about the entire context of the paper, because honestly, I was a bit like kind of like confused or kind of taken back, because first you started talking about how like microchips and how these chips are made and what are the rules, and then we went to zoom out to theories of consciousness, and then I was like, wow, this is like a huge difference in like jumping between levels of explanation. But then now with this, what you mentioned with the reduction, like this dynamic reduction, now I understand that you have this kind of like connecting material that is this dynamic reducibility. But then I wonder if you would agree with this kind of approach also in neuroscience. So let's say we assume that, like let's say with EEG patterns, we see like an electrophysiological fluctuations, and then in some way we assume that certain fluctuations are corresponding to consciousness kind of affects how these fluctuations unfold, or the temporal dynamics of the different spaces where this EEG or where like the electrophysiological signal could be. But then we would say that, okay, if consciousness affects EEG, then consciousness has to affect also on a single neuron level, because it should be reducible. Because if neurons are, if we would know all of the different neurons and how they are connected, and we could explain what we see in, for example, in the EEG level, on the whole brain dynamics level, then, and that is affected by consciousness, then the single neuron processing should be also affected by consciousness. Is that something that you kind of imply, or am I kind of over-interpreting?
I think we have different opinions on this end. But but Tim, maybe like if you promise that you say yours, I'll say mine. Do you want to go first, or?
Okay.
Yeah,
I can go first if you want. But
okay, cool. Yeah.
Okay. So if I understand the point correctly, then you say if consciousness is relevant for the EEG signals, then it would be relevant also for the neurons. Like that assumes, and I guess that's correct, but I'm not a neuroscientist, as you know, that assumes that the neural activity determines the EEG signal, which I just don't know, but assuming that that's the case. So if you knew all the neural activity, then you would exactly know the EEG signal. Then if consciousness is relevant, if consciousness is relevant to the EEG signal, then it must be relevant to the neurons, at least to some of them. I mean, we are not saying that it must be relevant, dynamically relevant to all individual neurons in that case. It's just there must be some neurons to which that is relevant, because otherwise, so you could not have consciousness dynamically relevant to EEG signals, but to no neurons if neurons completely determine the EEG signal. Because this completely determining step, like if you can derive from your neural activity the EEG signal, then like whatever is relevant for the EEG signal must be somehow relevant for at least some part of your neural system. If it wasn't relevant for the neural system, then the neural system would uniquely determine what's going on in the EEG signal without consciousness being relevant, right?
I think, sorry, and we don't have the different opinion. We have the same opinion. I thought
we have the same. Okay, cool.
Yeah. The reason I said that is because I think Tim, if I understood, I mean, we don't have to discuss this now, but so for me, it's very hard to really make sense of the idea that consciousness somehow plays a role in individual neurons. I'm not against this. I'm totally open, you know, if you have a theory. But the standard go-to thought for me is always just, how is consciousness dynamically relevant? Well, there's a brain function we didn't see before. You can imagine like a weaker version or more imaginative version where maybe there's a brain mechanism we didn't see, but that's a bit unlikely because we scan the brain quite a lot and, you know, people do good neuroscience. But a function is something more, oh God, what's the English word? Like more faint is the wrong word, but more intangible than a mechanism, right? A function could be carried out by several regions together, you know. A function is something very, very abstract. Maybe we just missed a function, you know, it's not in our model. So in that sense, I fully agree with what Tim said. Like we missed what a couple of neurons did, but not because like there's consciousness like in the neuron or whatever, but because these neurons were part of executing a function that we just didn't have in our model so far. That's my go-to standard example to think about, which is, it's 100% compatible with what you say, Tim. So some neurons must have done something that we didn't know, but not because like the consciousness played a role in the individual neurons, but just because there was a function we didn't see. Much like, for example, like your computer is doing something which you don't know, probably, and which probably people from Microsoft don't even know, because there's some, okay, this is a joke, yeah, but there's some weird stuff going on in your BIOS, which, you know, like has to do with something cyber intelligence maybe, and you don't know about it, you know. And so in that sense, right? Like,
yeah,
I'm not sure if that helped.
Yeah. May I maybe add on that, because I think I now understand where like the origin of the question, like why you are asking that, because like, or at least what you might be wondering about is, if that's true what we are saying, where is actually room for consciousness in natural science theory? So how can consciousness enter in there if it's not already in there? And like very briefly, we could say, like in natural sciences, there is room for consciousness wherever there is room for newly discovered natural sciences. Like wherever we don't know exactly that our descriptions are exactly true for what is going on in the system,
So
there is room for dynamically relevant consciousness. And in principle, I mean, from this argument, there might be ways to rule out that possibility from other perspectives, but from our argument. And then I think in that context, it makes sense to try to understand what's the difference between like these implemented formal systems and just natural systems occurring. So, and the key difference is the verification step. So here we have, on the one side, we have the formal rules, and then we have an implementation. So we build a physical system, and then we verify it to make sure that the physical system is doing exactly what the formal rules say. And if it's not doing that, we just say, okay, it's now a broken system, so we don't care. That is not what we do for describing like actual natural systems, like the brain, for example. We describe it, we have the brain, we describe it by a formal system, let's say by a theory for neural function, like what's going on, or neural mechanisms. But we don't know, we have no verification step. We are pretty sure, like it's a well-confirmed theory, I guess. So we are pretty sure it's rather good for a description, but maybe there are some tiny bits where like the prediction of the theory are not exactly the same as what's going on in nature. And these differences, that's at least some room for consciousness to come in. Whereas there is no such room for the implemented formal systems, because there we know by a verification step and definition of what this implementation is, like what's a working and like a properly working and a broken system. We don't have a room for consciousness coming in there. However, we do have a room for consciousness coming in dynamically relevant for natural systems, wherever like our deviation, wherever there's a deviation between our description of the natural systems and the actual dynamics of the natural system. So it might be a tiny deviation, but there's room.
I would say at the very least, there's room whenever there's weak emergence, at the very least, maybe more, right? Because weak emergence means that we're not actually in a capability to check that the higher level dynamics go back to the lower level. So maybe we've just got the higher level dynamics a bit wrong and we missed something, for example, related to consciousness. At the very least, whenever there's weak emergence, there's room for consciousness, but in practice, maybe more. You know, in practice, like, I think there are various views, but you can make the point that our knowledge about the brain right now is very good in the microscopic and macroscopic domains, and very limited both in terms of precision and in terms of like percentage on the mesoscopic domain. There's lots of rooms.
Okay, but then wouldn't this kind of argument mean that in case if we go back to the AI system, then if I have an AI system that I don't have a complete description and there's this kind of room for uncertainty, then we cannot really say, because we have this kind of unknown thing in the AI system as well.
Yeah, exactly. So, and this is exactly right. And this is a point. So first of all, like, this is related to something I study as well, model computation. I have one preprint out, but the actual progress, which is not written up anywhere so far, came again, as so often in my life, from discussions with Tim, where I really understood much better what model computation is, or could be at least. And the point is exactly this: like we can 100% make sense of computation that is not verified. In fact, if you look at the original idea from Putnam about computational functionalism, there's no verification whatsoever. He uses descriptions, probabilistic automata. So like there's lots and lots of room for consciousness to be computation and still be dynamically relevant. And so there's two things. So first of all, I think this points us towards another notion of computation, that's sort of where this whole verification step is missing. And then I think in practice, we see two different strands of developments which show that we're going to have these systems anyway. There's lots of startups that what they do basically is they try to produce analog computers that implement the current LLMs to make them energy efficient. So this is in practice, these are still semiconductor chips, but they're analog in the sense that they're not, they do the computation right on board. They're not like, they're not universal computers in that sense. And like some of them literally use like resistance to provide the weights of the neurons. So some of them are like super analog, other of them. But there's a whole industry about this. So we see it on that end, but then also we see it on the other end, where sort of the whole LLM architecture is basically reviving the vision of a computer we have. And two people who are very influential in that respect is Andre, I think, Kapati, who posts a lot about LLMs, wonderful posts and also videos. And I think he sees this too, that sort of we have this new paradigm of computation coming up, where what we used to think about the computation is now going to be, the LLM is going to be your operating system. Then in a very, very strict sense, also on the software side, we might lose this importance of verification. And Jeffrey Hinton is another one, like this feed-forward algorithm, which he proposes, where the original idea of model computation comes from, is essentially an algorithm that you can implement on systems where which are not verified, where you're not capable of carrying out exact backpropagation. So I think your point is exactly
sorry, I just a clarification here. So do you think that so what is the relation exactly between verification and mortal computation? Like mortal computation, like you cannot have mortal computation if you have verification, or how do you see the connection here?
I hope I get the logic right now. Tim, please correct me if it's wrong. But so if I have it right in my mind, it's verification implies immortal computation, or no, sorry, implies wrong. Verification is done so as to have immortal computation. So you could read this as implies, but it's actually the purpose of verification is to get immortal computation.
I would state I fully agree, but or maybe not about the purpose thing. Probably that's true. I don't know if I just don't know. But there's like a different way to view that is to verify an implementation. You need to have had a model which you implemented. So the verification step like tries to like rule out that the physical system is doing something different from what your formal system or your model is doing. And that means like whatever the model is doing, like that's actually the immortal part, so to say, like the model, because it's not even a real thing, so it cannot die, so to say. But like you have that model and you check if your implementation of that model is doing that what the model says it should do. And in that moment, like the verification step, because it's like relating the physical thing to a model, like says, okay, the model is immortal, so the computation must be immortal. It's always the same. If you use the same model, you get the same results. However, like, and that's a point Johannes worked out, is like the model computation is a model-free computation in that sense. So there is no model to be verified in model computation, or at least in model computation as we understand it now. So there's no model to be verified, and that means like there cannot be a verification step. There can be a description of what's going on in these model computational systems, but the description is different from a verification of the implementation. So it's like closer to this natural thing where our description might be extremely good, but there might be something which we get wrong and we will never know. And that's basically the difference between model computers or model-based computers and non-model-based computers. And it's, as we understand, basically the same differences between mortal and non-mortal computers or computations. I hope that's...
So you could say that to verify is to make immortal, if you want to summarize in a slogan.
To be model-based is to be immortal, and you can only verify something that's model-based, because like you need the model to compare. But in a way, yes.
Try to sell a catchy slogan for this proposal, but yeah, I got the point. Of course.
I basically agree. Just I want to say it's not to make immortal; it's just realizing it was immortal all along.
Yeah, so just like we forgot one question, I think, by Angus. Let's come back to that in a second. But one last thought on this whole thing. So the way I see it really, like, and this is, so the way I see it is that we have this paradigm of computation, which was extremely influential, like in our whole society, in our whole world. And I think the question that's coming up both on the sides of LLMs and then also perhaps on the side of consciousness is whether there are other things you could actually mean by computation. And I mean, of course, like we have other models of computation. I'm not at all an expert. I mean, in fact, I know very little about this. But for example, Lenore's work, Lenore Bloom's work, life work, I would say even, is a model of computation over the reals, right? So there are already a bunch of different models of computation. In philosophy, we have neuromorphic computation. Then I think there's neural computation. There are a bunch of slightly different notions. But I think in philosophy, most of the notions still somehow tie back into the original mindset of like Turing computation, even though they violate a few things. or maybe not, but probably some is gonna disagree with that very hardly in the comments. I take it back maybe. But what I'm saying is, like, I think that I think a very legitimate quest right now in consciousness science, and if anyone had ideas, I think this is, in my view, that's super important work, is to try to even think about what it would mean to come up with different notions of computation, or to be more clear. I think that, okay, so this is a slightly different topic, but I think, so if we look at all proposals right now, which are concrete proposals, which are trying to propose theories so that AI can't be conscious. I'm not saying we should, I'm just saying people do this, and there's an interesting epistemic problem. Then what we see is the only thing that we can do, on my view, or based on the knowledge that I have right now, we can only point and say, it's like, for example, Ned Block, he says, well, you gotta have electrical and chemical, right? But that's a proposal that just works by reference to material stuff, which isn't in the AI, in this case, chemical, right? Or there are other proposals, like concrete proposals. They literally just say, well, it's got to be some stuff that is not an AI system. So my challenge would be, can we actually come up with a theory that doesn't do that and still prevents AI from being conscious? And so the question that is can we actually make a sort of a substantive understanding of consciousness such that it's not just about information, or if you like, I don't even know what to say. I don't want to say like computation, but it's can we? What would it mean substantively to say that consciousness is not just about information, other than just pointing to like material stuff that isn't AI? Maybe there's a very simple answer to that question that I'm just not seeing. That could be, but it seems to me that like this would be a great achievement, even to understand what it would mean. And I think what this would amount to ultimately is trying to. We have these computational glasses on. Even neuroscience is fully an information theoretic discipline. It's in a sense an application of Shannon and Turing's work. That's what we do in the brain. And there's always the danger that when we do this, that we don't see stuff. And just because we have these glasses. And so my question would be like, even though keeping on the glasses, can we still even make a concrete conception of what something would be that we couldn't see with these glasses? Yeah, and I'm super interested in that work. I think this would probably lead to conceptual progress that is on a par with Putnam's definition of functionalism, computational functionalism back then, right? Which was a completely new proposal that now we struggle to like it's everywhere. It's very important. I think these things are good. Yeah.
Well, I obviously have a provocative question now that you said that, yeah, and could an IIT be such thing that you are asking for?
So I think in IIT, so on my view, IIT is still a completely an information theoretic system, and so what you can do is you can apply IIT to like any sort of AI system or computer, and if I understand correctly, which maybe I'm not, but if I understand correctly, the reason that in IIT AI systems can't be conscious has to do with the specific architecture that is applied. Basically, because of this, what's it called, coarse graining that you have. So basically, the IIT algorithm says, well, you can't just apply IIT at a specific level, but you have to go through all levels and choose the one where the phi is the most. So the question is, if I run a program that simulates a brain, why can't I just go to the level where the coarse graining is that it would be on the actual brain, just like in terms of the virtual units, in which case the simulation would be conscious. And according to my understanding, in IIT 3.0, if you take everything that starts with the 3.0 paper and that ends with what's before the space is what does it feel like the space feeling paper, according to the whole formalism that's presented there's nothing that prevents you from doing that. There is, however, in 4.0, and apparently there's a paper before the 3.0 paper that Justin pointed me to, didn't read it so far, that gives limits on the sort of coarse graining you can do. And these limits ultimately imply that you just can't choose the right coarse graining, right? There's you can, if you start, let's say on your microprocessor level, right? Or let's say in the transistor level, and you try to go bigger and try to see if phi somehow pops up large at some point. At some point, you can't go further. Even so, if you were just to randomly choose a coarse graining, like a specific coarse graining, you could choose one where the system is not conscious. So what I'm saying is that IIT is still like, it wouldn't satisfy my requirement that I just put out because it's still a fully information theoretic theory. So the reason it's not that, like, we could easily build AI systems that are conscious if we just go away from the typical CPU design that's like just build other CPUs, like no clock, for example.
I see. I don't want to make this meeting about IIT, but thank you for your input on that.
Thanks.
I think Aniko had another question, maybe. Or Angus, sorry.
I think Angus, yeah.
Yeah, on the difference between dynamical relevance and causal relevance. So far it sounds kind of the same. So it would be good if you could just like give a simple example of like where they're clearly different. That would help a lot.
Tim, do you want to take this, or should I? Or
if you have a specific example, so I would have temperature in mind, but I am still 100% sure if it's a really good example. Maybe you have.
Maybe I can answer an abstract, and then we can consider your example, because that might help. So I think there's 2 important points. The first point is causal closure or violation of causal closure. That's a metaphysical condition. So that's not what you asked. I'm just saying this. So if someone says the physical is causally closed, they mean that there's something like, for every physical effect, there's a sufficient physical cause. The definition doesn't matter now, but they basically are saying there's nothing that's non-physical that has an effect. But that's completely compatible with there's something physical that has a new causal effect that we didn't know before. In fact, all of foundational physics is premised on this. We're trying to find new physics beyond standard model, whatever, dark matter, whatever. We're trying to find new physical things that explain, that have effects among the things we know, which we didn't know before. So causal closure and dynamical relevance are 100% compatible, right? As soon as you say whatever I'm introducing is something physical, you automatically, like, you satisfy causal closure just as you did before. Like, one word again on the opposite direction, like if you're saying, well, there isn't causal, like the causal closure of the physical is violated, meaning now you're saying there's something non-physical that has an effect on the physical, that does imply that whatever violates the causal closure of the physical is dynamically relevant. So the concept is not completely orthogonal. Like, if there's dynamical relevance, if there's causal closure, you can or cannot have dynamical relevance. If there's violation of causal closure, you can only have dynamical relevance. You cannot have dynamical irrelevance. So this is the first thing. But this is not what you asked, because you asked about the causal effect. Now we can say, let's drop this whole metaphysical discussion and stay right within the physical and ask, is there a difference between something having a causal, is the word you use causal effect or causal relevance? Causal relevance.
Causal relevance, yeah, I think.
Yeah. So let's say we have something, like, for example, in this car example, we put something in the back, in the trunk. Does this something have a causal effect on the car? And there's as far as you can see now, there's 2 dimensions, or 2 distinctions that are relevant. So the first distinction is causal relevance is usually framed more in terms of like what's actually the case in the world, whereas dynamical relevance is really just about theories, right? It's a concept that's we've explicitly made this concept so that you have to say which theories you mean, and then then it holds. It's a property of one theory with respect to another. So that might not be so important, because you can say, of course, well, those are the real theories, I mean, or whatever. And so the second dimension, and that's much more important to me, is there's the substantive question, and discussed a lot in philosophy of science, what actually causality is. And there's a huge amount of options, and they have extremely different properties, whereas many people in philosophy of mind, for example, think that causality is like somehow something fundamental. Most people, I would say, in philosophy of science think of causality as something that's not fundamental, because of extremely influential work by Russell, for example, and then other work that builds on top of this. Most people think of causality as something which is more like an epistemic tool, rather than the fundamental web in which the universe is cast. So there's this whole range of ideas about what causality could actually be. And my claim would be, I never like can't prove that claim, or didn't go. I did go through a bunch of examples in another paper once where I didn't have the concept yet, really. But my claim would be that whatever you say that causal relevance is, it implies dynamical relevance. Dynamical relevance is like the weakest possible thing you can have, which is implied by all of the ideas about causality. It's like, in other words, like if you don't, yeah, okay, no, I won't try to defend it. But so I think it's first of all, it's a different notion because it targets it's targeted on theories. And the reason, I think one of the reasons we did that, we formulated in terms of theories, is because dynamical relevance of a theory of consciousness with respect to like some reference theory is something you can, when you start making theories of consciousness, it's a question that you can always answer. I'm making a theory. Am I saying there's something new in neuroscience or not, right? Am I saying that's there already and now this is just consciousness, or am I saying you guys missed some mechanism or some function? And causal relevance is not about theories primarily. And then the second difference is that causal relevance is like causality is something various different understandings. They're different with respect to important things. And dynamical relevance is like the most minimal condition you can get away with.
Okay,
Tim,
I think I understand it all better.
Okay, yeah.
So if you want, I can try to discuss it at this, like with the circuit example and temperature. So maybe that helps. Let me try to draw it. Let's say we have a voltage source somewhere here. We have an ampere meter somewhere here. So this is measuring the current. This is applying a voltage. And then we have some resistor here. So this, and we know that the voltage is equal to resistance times current. This is Ohm's law. And now the point is that the resistance of a resistor can actually depend on temperature, or it usually will depend on temperature. So the higher the temperature, the larger the resistance. Let me maybe draw that as well. So let's say we have some temperature, we have a resistance dependent on temperature, and then let's say we have something like this. So the higher the temperature, the higher the resistance, very roughly. And now let's say we want to have, have I of t, like the current dependent on time, how it depends on time, given some voltage, like given v of t, like how we apply the voltage dependent on time. Now, one thing you also need to know, one thing you also need to know is if you apply a current, like if a current is flowing through a resistor, it's actually like there is resistance, at least for typical ohmic resistors, there is resistance because there's some dissipative processes, meaning it's actually giving energy from the charge current, so to say, to the resistor, meaning it's going to heat up the resistor. That means we apply some current or some voltage, causing a current flowing through the resistor. It increases the temperature of the resistor, and thereby it increases the resistance. And now you might ask, or what we can say is the temperature of the resistor will be dynamically relevant for the current flowing, right? Because if the temperature is higher, the resistance is higher, and thus the current will be lower for the same applied voltage. So the temperature coming from like a concept from thermodynamics is relevant, dynamically relevant for the charge current from electric circuit theory. However, you might also now want to ask, is it actually causally relevant for the current flowing? And then the situation becomes less clear. So if you just stick with these two theories, at least. Why is it less clear? Because if you say, okay, the flowing current increases the temperature of the resistor, then actually the current is the cause for the increased temperature. So the temperature cannot be the cause for the change in current flowing. So like there is some, like, while dynamical relevance is some abstract concepts relating some concept relating concepts of theories with each other. Now we are asking for what's the true cause? Is now the flow of current causing the temperature to rise, or is the rising temperature cause the current to flow differently? And like the question is where to put like the cause here. Like what's the cause, what's the effect? That discussion you don't have for dynamical relevance. And that's like a key difference why dynamical relevance is a more general thing to apply to theories, let's say, rather than this. So you're not committed to some ontological statement, or not as strongly as for causal relevance. So the dynamical relevance is a property on the epistemic level, whereas the causal relevance would be a property on the ontological level, or ontic level. And yeah, that I think is a key difference. Now, specifically for that example, I think we should call the temperature actually causally relevant for the resistance, because there might be other effects changing the temperature. So it's not uniquely determined by the current flowing what the temperature is. So there's actually lots of other stuff determining the temperature, in particular, like the temperature of the environment, which is important for determining the temperature of the resistor, and not just the current flowing or the dissipative part there. But I hope that clarifies like the difference between dynamical relevance and causal relevance.
Yeah, so just to check my understanding, with the causal relevance, there's a sense of like direction as to what's causing what. Whereas with dynamical relevance, there's just some sort of difference, and it's you don't need to assign what is causing anything. Okay. Thanks.
Yes, exactly.
Well, since you guys are also philosophers of science, I think it would be super interesting to maybe not now, because I also feel my brain power is draining and it's only 10 m for me. So for Aniko and Angus, they're probably much worse. But it would be super interesting actually to take a step back and abstract from consciousness and think about this dynamical relevance in relation to the holistic underdetermination problem in philosophy of science. Because actually, the more you were speaking, the more it seems to me that there, of course, I would have to think more about it, but it seems to me that this could actually provide some significant insight in this very classic philosophy of science problem, which basically tells that it's very hard to disentangle empirical observation from theoretical statement, because the two, like one always inform the other, right? Basically, you never have an empirical observation that is just an empirical observation, but an empirical observation is informed to a certain extent by some kind of theoretical statement. So whenever you actually test a theoretical statement and you have an empirical result that contradicts your hypothesis, you never really know if which side of the theory, so to say, like the one you're testing or the one you're using to read the result is the one that has gone wrong, right? And this is a very essential summary. But I think this idea of dynamical relevance could actually be very interestingly applied to that kind of discussion. But maybe we can keep this conversation going in the future.
Yeah, it would be great to continue discussing that at some point. I think indeed, like now opening that would take too much time, but I very much like the idea. I think like just very brief first intuition is, I think that the most important step in solving that problem, so to say, is introducing different theories. That like it's not just like holistic for all theories of natural sciences, but we have like we need to take into account like the process of how a theory is developed and which are well established and then which are tested and so on. But I agree that dynamical relevance seems to be an interesting concept to apply to the problem. Yeah. Thanks for the suggestion. Looking forward to this.
I think that would be also not but just it would be super interesting also for just in general, like psychological and also just neuroscience methodologies, and also with the adversarial collaboration and adversarial approaches to theory testing, because that's literally what's happening in many cases, that people maybe don't agree whether we are testing the theory or the implementation, and then like if we cannot agree whether we have like a proper technical implementation or like a practical implementation, then we cannot possibly compete or compare between theories. So yeah, I also agree that it's a super interesting question and might be very useful for a general kind of discussion as well, but also for consciousness, consciousness and neuroscientific consciousness research at this time.
Yeah, thanks.
Yeah, fully, yeah. Yeah, I think I mean, more general, I think that consciousness science, independently of this, actually, I think that consciousness science is like, the problem of consciousness is so specific and in a sense so hard or so involved that it is very likely that we're gonna turn the tables in a sense. So far, consciousness science like just used concept developed in other sciences, mostly at least, you know, and perhaps at some point it could be the other way around, that much like, you know, quantum physics, when it was the frontier of science, it still is, but like it provided a lot of cool ideas and ways of thinking, and perhaps consciousness will be that, will serve that function in a certain sense at some point. Yeah, but thank you very much for like holding on. So I know that, you know, lecture about resistors at 12 at night, that's quite a mouthful, or how do you say, like quite challenging. Yeah. So thanks for
great.
It was great. It was great. It was generally great. I was just being honest on the fact that I realized.
Yeah, no, fully.
Attention.
It was the same for me, you know. Yeah.
Yes.
But,
okay. Should we stop or close things down?
Yeah. So thanks everybody. Thank you, Johannes. Thank you, team, and thank you, Aniko and Angus. And thank everyone who is watching this video, if anyone. And well, maybe to the next paper.
Yeah. Thank you again.
And
thanks for reading the paper and for the question and the interest. Very much appreciated.